Do my project on female heights and their shoe sizes. You can see here that we start off with about 87 data points, and then we narrow that down to 30 data points over here. And then for my summary sheet, I chose to do female heights. And then we found the Z-score of each of those heights. We have a minimum female height of 52, maximum of 72. And for our classes, we did 7 classes with a width of 2.9. For our mean, we found that it was 63.983, so that would be inches tall. And then we have a mode of 65, mid-range is 62, range of 20 different values between 52 and 72. We have a variance of 19.250, standard deviation of 4.387, a covariance of 6.857, minimum value of 52 as well up here. We have fourth quartile of 62.25, medium of 65, third quartile of 66.75, maximum of 72, and you can see that down here as well. And then your inner quartile range of 4.75, lower fence of 55.5, upper fence of 73.5, and our outlier values, which are 52 and 54 inches. And then you can see that over here as well. And then you can see on my histogram over here that the distribution is approximately bell-shaped. You can see the little bell figure there, with a small left skew over here due to the 2 outliers. You can see that there's 2 in there of 52 and 54 inches. I have a single mode of 65. And then you can see from the histogram that the only one bar graph is that tall, and there's no other bar graph that is the same height of it. And the most relevant measure of center would be the median, because it is resistant from all the outliers, 52 and 54, whereas the mean, for example, is pulled towards the left because of the outliers. And the measurement closest to the mean of 63.983 would be 64 inches, and you can see that over here. And since the standardized value, or Z-score, tells us how many standard deviations the value is from the mean, 64 has a Z-score closest to 0. You can see all the other ones have either lower or higher Z-scores, and this one is closest to 0. And then the only data that is beyond the 2 standardized deviations from the mean are my outliers, 52 and 54. And based on Chebyshev's rule that at least 75% of the data is within 2 standardized deviations of the mean, our sample set exceeds the minimum with 93.3%, or 28 out of the 30 data points within 2 standardized deviations. Moving on to our confidence interval. So our confidence interval, you can see that there is a count of 30, so 30 value points. And then we are trying to figure out the percentage of adult females that are over 62 inches tall with a 90% confidence level. So you can see that 22 of those value points are over 62 inches tall. And then we went on to do the sample proportion, which is 22 divided by 30. 1 minus the sample proportion was 0.2667. Sample size of 30. We have alpha of 0.1. Critical value of 1.64485. Our margin of error, which is 0.13280. 0.005 is the lower interval, and we have an upper interval of 0.8661. And then that means that I'm 90% confident that the true population of females taller than 62 inches lies between 60.05% and 86.61%. In other words, if I were to take another sample set, then roughly 60 to 87% of those females would have a height taller than these 62 inches over here. And while that exact percentage is unknown, I am 90% confident that the true value is somewhere in this range right here. On to the hypothesis test. I tested the claim that the mean height has significantly changed from what it was in the 2018 CDC report, which was 64 inches tall. So my sample mean for this was 63.9167, sample standard deviation of 4.2752, sample size of 30, alpha of 0.05, and for my test setup, my null hypothesis states that the mean average height is 64 inches. My alternate hypothesis states that the mean height is different from 64 inches. And then you can tell I have a two-tailed test, critical value of 2.0452, standard deviation of 0.7805, test statistic of negative 0.1067, and a p-value of 0.9157. So using the significance value of 0.05 over here, the p-value was 0.9157, which is a lot larger than the alpha that we have over here. Therefore, I failed to reject the null hypothesis over here. So my sample does not give sufficient evidence that the average female height has changed from 64 inches. Moving on to our correlation test. So we were asked to determine if a significant linear correlation exists between the shoe size of a female in the US wears and their height. So for my correlation coefficient, I found that it was 0.7497. And since that value is very close to 1, I mentioned that it appears that there is significant linear correlation between the shoe size of a female in the US and their height. And then in my scatter plot, you can see that the x variable is the female height, while the y variable is the shoe size. However, for the first prediction, right over here, you can see that I was trying to find the value or the height of a female who wears a shoe size of 10.5. So the shoe size is the x variable. Then for my next question, I estimated the shoe size based on the height. And since correlation is symmetric, either one can be used as x or y variables depending on what you're trying to predict. And then over here, which of these estimates would you tend to believe more or why? I would believe more of the female who wears a shoe size of 10.5 because that shoe size lies within our data value range. And predicting the shoe size for a female who is 75 inches tall is less reliable because 75, you can see, is outside of our data range, making that extrapolation. So overall, my project found that the sample distribution was approximately bell-shaped, the slight left skew. The median of 65 was the best measure of center due to the low effect from outliers. For my confidence level, I'm 90% confident that the percentage of female adults that are over 62 inches tall would lie between 60.05% and 86.61%. I found that there is no evidence that suggests that the average female height has changed from the CDC's report of 64 inches tall. And from a correlation test, there is a strong positive relationship between female height and the shoe size, and you can see that positive relationship right over here. Thank you for watching.